Okay. So hi everyone, I'm Sander. I'm a graduate student at Ghent University. And I'm basically the lead developer of Psiflow, which is a package for atomic simulations. This is basically going to be a talk about a developer trying to build something with Parcel for users that are not very, let's say, computer experts. So first, like, what do we want to do? So if we take the most simple example in atomic simulations and predicting physical properties, let's look at the hydrogen molecule and its IR absorption. So hydrogen absorbs IR frequencies. And if we want to figure out which specific frequency it's going to absorb, then in molecular simulation, what we would do is we would start from a certain atomic configuration of the hydrogen molecule, compute the energy and the forces on it, and we would propagate it across a certain finite time step. And we do this multiple times, so multiple force evaluations. If you repeat this throughout time, then that allows you to basically estimate the absorption frequency of hydrogen. And this is a very trivial example of physical property estimation, but you can generalize this across a lot of different systems, be it, the water-ice phase diagram or the stability of certain perovskites in solar that are being used in solar cells, or heterogeneous catalysis, in this case, zeolite catalysis. So in general, free energy calculations, reaction rate calculations, they all come down to millions, billions of energy and force evaluations. Now, from quantum chemistry, we have a bunch of techniques that allow us to compute these forces between the atoms, but none of them are, or not all of them are equally accurate. So if we plot these versus their computational scaling, then we see that only the force fields are really at exhibited a computational scaling that is more or less feasible. But the ones that have the accuracy that we need in order to be predictive are much, much more expensive and are really not feasible. And so in recent years, what people have been trying to do is they've developed neural network models that can basically learn this complex function that goes from atomic coordinates to final potential energy and therefore also gradients. And they do so using equivariant features and equivariant neural networks. The basis of this was laid in 2018, but they've really grown or have been adopted in the community in the last 2 years or so. And so this is basically what Psiflow aims to do, is make the development of these potentials easy to do by the user. And so in pseudocode, what the workflow that we would like to perform is basically we have a certain model, a certain equivariant neural network that is predicting our forces, but it's not really trained very well. And so in an active learning loop, what do? We generate some atomic configurations using this model. We use molecular dynamics or some other sampling procedure. We evaluate the DFT or with some other reference level, the energy and forces that we want to learn, and then we train our model onto it and we repeat. And then if you look at the computational infrastructure that's needed for each of these steps, well, depending on which step you're doing, it's either CPU or GPU. But if you go a bit more fancy, if you use more fancy post-Hartree-Fock methods to be more accurate in terms of the energy, then you're going to need large memory CPU nodes. You might need more GPUs to train more complex models. Anyway, it becomes very, very complex. And this is, of course, why something like Parcel is necessary. And so in Psiflow, basically, the sort of the key assumptions are the average computational chemist is not very computational. So I try to hide as much of the Parcel API as possible. And secondly, write once, run anywhere is really elegant. And so I forcibly separate every type of execution configuration from the high-level workflow definition. So how does this work? So the pseudocode that you've seen just before, that's sort of implemented with high-level abstractions, a model, a trainable model, a data set of atomic configurations, a walker that implements phase-space sampling, and a learning method which defines active learning parameters. That's sort of in a main Python script. It's usually just 100 lines or so. But then everything else on the execution side, which is not just Parcel providers, but also parallelization parameters, the precision of your neural network, certain wall time limits, and possible containers that you're using. All of that is then defined in a separate Python file. This could actually be a YAML file, as the first talk mentioned. That's actually a good idea. But anyway, for now, it's a Python file. And so if you run the main Psiflow script without any arguments, it's just going to spawn a bunch of threat pool executors with reasonable defaults. If you do, however, give a configuration, it's going to use that configuration, load it, compile the apps, and run on the specified resources. So now in terms of actual code, just to give you a very, brief look at what everything is. So the high level abstractions, they basically wrap around app futures or data futures. The first things first, so you have parcel.load. Well, now you have Psiflow.load, which does basically the same thing, except that it does a few other things as well. But then we can load our data set of DFT reference data. We initialize a model and we can train it. And so even though the user does not immediately see that he's working with Python apps and futures, that's basically what's being done in the back. The parcel graph of dependencies is built in the back. Of course, in the end, you do have to expose the user to results. I mean, script generates a result. That result is going to be a future. And so there is a minimal, let's say, interaction between parcel and the user. So in this case, a NumPy array of errors. So Psiflow has a bunch of dependencies, so I found it very useful to package all of them in a Docker container, which meant that I had to subclass the launcher and make a containerized launcher. And I'm running out of time, so I'll just close with a few remarks. We've noticed that when we run big workflows, we create huge amounts of files. And something that I want to look into is automatic tarring or automatic archiving, because otherwise the HPC administrators are complaining. Similarly, big workflows require a lot of memory in the main process. For some reason, this could also be due to our bad implementation, but I was wondering whether on disk or aggressive paging or something is an option. And I think lastly, most of the users in Psiflow have a lot of trouble debugging parcel workflows because the errors can be spread around at different locations. One thing that I would like to note is that the lazy failure might not be a good option in all cases. Sometimes you want failures to be caught by the code itself, and that any other errors that appear immediately you have to stop the entire workflow. That's just a thought that I'm having. Anyway, these are the people that I work with, and I'd like to thank you for your attention.
Great, thanks for that. Also within 5 seconds of the appropriate time. Does anyone have questions in the room or on Zoom?
Yeah, hi Sander. This is Logan Ward.
Hi. Yeah.
Where does the kind of integration between the AI and simulation sit? I saw you've got an active learning loop.
Yeah. So it sits here. Let me go back. You still see the screen, right?
Yeah.
So it's here.
So does this live as part of that like run.py script the user writes out this kind of continual loop inside of it?
Well, no. So the interaction is basically that you use the model to perform molecular dynamics.
Okay.
So the force field, so the predictor of the energy and the forces which you need to propagate your system at each time step, that is given by a neural network. And that's the neural network that is trained in an active learning loop, if that answers your question.
I think it does, or at least it's getting close. So this loop you're talking about here, where you generate data and then train them again, is that part of, I saw you had this run.py notion? Yeah. Is that where it lives?
Yeah, that's exactly. This would be in the run.py. This is, of course, a bit simplified, but yeah, that would be in there, yeah.
Okay, no, it makes a lot of sense.
Yeah.
Cool stuff.
Yep.